Okay, so we are now moving on to uh, section 2.3, which is vapor pressure and cavitation. And I have a little cartoon here. It's kind of a weak one, I think. I don't know. Where you could see they have the gauge on top. The vacuum is unplugged, and we have wetted is inside this jar. But we plug the vacuum cleaner in, and it creates a vacuum, and whoomp, heat transforms into vapes. That's the idea of vapor pressure and cavitation, is that if the pressure gets low enough, even at room temperature, a liquid can become a gas. Pretty pictures of stuff. We could think of that, above the vapor pressure, but like at room temperature, we can still have a state where we have some amount of water vapor and some amount of liquid phase, right? This diagram right here, where we have maybe a liquid with a sealed kind of a little plunger cylinder piston in here, and if we lift it up, there's going to be a gap, right? Because the liquid's not going to expand. So what in that little gap, if we lift it up, that would be what the vapor pressure inside there. It would become the vapor pressure. Another thing we could do is we could take, let's say, a glass tube and submerge it all the way in the water. So what we see here would be like a little deceptive, right? I would want to make this bath right here deep enough so I could completely fill up this tube with all complete water, and then lift it up vertically, and then pull it upwards, and then inside this tube would be the vapor pressure of the liquid. A lot of times it'd be so small that we could actually consider it to be zero, and then we could actually use this diagram is actually for a barometer, right? But that would be what the vapor pressure is inside there. And one of the areas where we see as an application, or we won't even say an application because it's bad, is when a propeller is moving at the correct high enough velocity. There could be regions where the velocity is high enough that the pressure drops low enough, and that low enough pressure will cause it to change phase, and this is called cavitation. And it can be very, very bad because it's not it's almost like a itty little tiny bit of an explosion that's taking place. These we want to call them bubbles, but they're not actually air bubbles. They're steam bubbles. These are actually steam, and the formation of them is not. It's not it was not a silent thing. It actually makes noise. Is the cavitation? It's a pretty rough thing, and it can actually wear out the surfaces of a propeller. And it also happens in pumps, where we can a pump where the vacuum, especially on the suction side, goes so low when it's sucking onto the thing that it can start to cavitate, and that can actually destroy the impeller on a pump. So it's sort of an interesting thing. And we want to find this information of like, well, okay, we need to know what the vapor pressure is so that we can know that we don't want to go below the vapor pressure. And in your textbook in Sengel, we have table 2.2, which presents, just a rough kind of temperature versus saturation pressure. You could see right around 30 degrees is probably the one I'll use. I have like a short example. And you can see that they have 3.25 kilopascals. You could see that over here in the appendix, and so this is just a little corner of the larger table on that page. It's in the page in which I got this, it was page 888, but I think in your textbook is a different one. I'll open up the book in a second. You could see a little bit more, another sig fig right in there of 4.246 kilopascals is the saturation pressure. And then Let's see, 30 degrees. That's a lot higher, I think, than of the segment I captured in here. But you can see where it is in PSI-A if you have a particular temperature. Did I have anything else in here as a slide? Oh no. Okay, here you go. Yes, in the liquid tables that you have for your for exams, right? So this comes out of Munson. It's the excerpt that we'll use. Here's where the vapor pressures are for particular things, but you can see that water is right in there. And there's at 60 degrees Fahrenheit. You could kind of compare where that is. They're saying that's like 0.256. So let's come back up to here, up into your book, and see, whoops, right in there, 2.563, right? So what did we say it was in here? 2.56, right? Okay, so it's the same thing, 0.256. And then, let's compare this one, what it has in this table. We're in newtons per meter squared, which is just a Pascal, right? So we have 1,770 pascals, so 1.77 kilopascals, and that was like in the 15 degree range, 15.5 degrees for whatever reason is what they're saying is they're using as the standard there. And so you can see they have about the same thing, 1.705 as opposed to 1.77. So let's see, we got anything else in here? Nope. So let's move over to our camera and go through our notes. Did I mention this was class 2? I think I forgot. This is class 2 video 3. Yeah. So it's going to seem out of context there because I didn't mention it. But anyway, I think you should use lowercase p, but this for whatever reason with a subscript v for the vapor pressure. And this is an important topic when it comes to pumps and piping systems, but also propellers. And as I mentioned, if we lift up this piston right here, we will get the vapor pressure in here. And so this is something that we look up, right? So we look up the vapor pressure. And it's really sort of the boiling point at atmospheric, that's, I guess maybe the boiling point is atmospheric. I'm sorry, I should have said that, right? So the vapor pressure at the boiling point, so like at 212 degrees Fahrenheit, that PV is equal to 14.7 psi. And we could prove that to ourselves if we take our book right here. And we flip to the appendix, and of course we have two separate appendices in terms of appendix A. Let's see, I'll go to E. Was it E? Yeah. So I think it's like right in there. You can see that I write in my book a lot. See, so I actually did that little conversion back there that I just said that I was doing. Write notes to myself in it. But yeah, 212 degrees. Yeah, they have that right there, right? So that's, let's see, get that big enough so you could see it. If you could focus, 212, come on, focus, is the vapor pressure 14.698, right? So, and then you could do the same thing if you wanted to in the SI units. Let's see, it should be like right there, and we're looking, and I don't know why I know why I did that. So you can see that it's 101.33, pretty close to atmospheric pressure, right? So boiling point thing to remember. Giving you a tour of the book, because the book is really important. You should really buy it. Sengel, great book. So like here, I say something that we should note: as the T goes up, the pressure, the vapor pressure, goes down. Is that true? I don't think that's true. The temperature. Let me think about that. I think I'm going to say the other way around. Yeah, I wrote that. I don't even know why I wrote that. Yeah, it's not a very good thing. Yeah, you could see it. You could just see it as the temperature goes up, the vapor pressure goes up. So basically, the thing we want to know is that liquids begin to evaporate. At the vapor pressure. So they could actually, maybe even should say they don't begin. They can expand immediately into their vapor pressure, and of course, it's that jumping from phase will create it'll expand quickly, and that's one of the reasons why it makes noise and it can be destructive. A process, because it expands quickly, the density increases dramatically when it jumps from the liquid phase to the gas phase. So here is a brief example. Say in a water distribution system, the temperature of the water is observed to be as high as 30 degrees Celsius. Determine the minimum pressure allowed in the system to avoid cavitation. Now, some of these allowed is a loaded word. We have to be, so I would say, first off, I'm going to look up and find out what pressure, the vapor pressure here, but then I might like apply something to this, right? The so-called safety factor. So if we're going to say what's allowed to happen, we don't want to make it exactly when it's going to happen. We want to have some kind of margin, maybe. And the people who determine that margin, well, it might be your boss. It could be you. It could be some code or standard. So we need to have that margin, which is called the safety factor. So if we look up from table A3 right here, for 30 degrees Celsius, right? We just had it open a second ago, so we could have kept it. You could see that I underlined the answer in my book because I wanted to. I'm going to try to do all this much more briefly in class, just so you know. So the videos are really here to help you if you miss something or you want to hear it again, you want to check it out. So anyway, I'll probably go through this pretty quickly in class, hopefully. It seems like I'm taking a long time. So for 30 degrees Celsius, it's 4.246 kilopascals. So we'll write that down. It doesn't equal this, but I would get 4.246 kilopascals. But we want to go P minimum. This would be the minimum pressure we're allowed to get it into, right? What we really need to do is we want to have this to be a larger value so that it doesn't cause cavitation, to avoid cavitation. So let's multiply this by a safety factor, right? Let's select or assume the safety factor is 1.5. So we're going to take 1.5 times this. We could double it maybe if we wanted to. So I'm just going to take 1.5 and the 4.246 and say that ends up with 6.369 kilopascals. But that doesn't make sense to make that like posted onto maybe in the system says do not allow, like a little placard says do not allow the pressure to go below this level right here. It wouldn't make sense to use that number. So let's say 6.5, and we could put a 0 in there, I guess, and we'll call it min. Allow. So it's the minimum allowable pressure for this system. That's just an example, but we will use this vapor pressure later on when we do piping system design when it comes to the suction of the pump, because we don't want it to cavitate. And there's something called net positive suction head, and so we'll be returning to it. It's going to be way later in the semester, but it's a good time to talk about material property or fluid property, and this is a fluid property you need to know about. Thank you, and that was end of video 3.